Scientists may have found the particle that explains why matter has mass. Exotic particle state may reveal the hidden origin of mass. A newly observed exotic nuclear state may offer an important clue to one of the deepest questions in modern physics: why do particles have mass? Researchers have reported evidence for a rare bound system in which an unstable particle becomes temporarily trapped inside an atomic nucleus. If confirmed, this phenomenon could provide direct insight into how mass emerges from the underlying structure of the quantum vacuum. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. The study suggests that some particles may become lighter when immersed in dense nuclear matter, supporting long-standing theoretical predictions that mass is not a fixed intrinsic property, but can depend on the surrounding environment. Published in Physical Review Letters, the findings may represent a significant step toward understanding how the strong force and the vacuum of space contribute to the mass of ordinary matter. Mass is more mysterious than it seems. Although mass appears to be a basic property of matter, its true origin is subtle. While the Higgs mechanism explains how fundamental particles such as electrons acquire mass, most of the mass of visible matter, such as protons and neutrons, comes from the dynamics of quarks and the strong nuclear force. In quantum physics, even empty space is not truly empty. The vacuum is filled with fluctuating fields and complex interactions that influence particle behavior. Understanding how this vacuum structure generates mass remains one of the central challenges of particle physics. One promising route to study this process involves creating unusual systems called mesic nuclei. What's a mesic nucleus? A mesic nucleus forms when a meson, a particle made of one quark and one antiquark, becomes bound inside an atomic nucleus. Because mesons strongly interact with nuclear matter, they can act as sensitive probes of how particles behave in dense environments. These systems are rare and short-lived, but they provide a unique laboratory for investigating how particle masses may change inside nuclei. The newly reported candidate belongs to a particularly interesting class involving the UAG eta-prime, meson, an unusually heavy meson whose mass is thought to be closely linked to the quantum vacuum. Why the meson matters. The meson is scientifically important because its large mass cannot be explained solely by ordinary quark interactions. Instead, it is strongly connected to deeper quantum effects involving symmetry breaking and vacuum structure in quantum chromodynamics. Many theorists have predicted that when the meson enters nuclear matter, its mass should decrease. Detecting such a shift would provide rare experimental evidence that particle masses can be modified by their environment. This would help clarify how much of mass arises not from particles themselves, but from the invisible quantum properties of space. How the experiment was performed. To search for this exotic state, researchers carried out a precision experiment at GSI Helmholtz Center for Heavy Ion Research. A beam of high-energy protons was directed at a carbon target. In some collisions, mesons were produced and became temporarily trapped within the carbon nucleus, forming an Ichibei mesic nucleus. Scientists then analyzed particles emitted from the reaction, especially deuterons and energetic protons, using advanced detector systems including the fragment separator and the Wasa detector. By reconstructing the energy spectrum of the reaction products, the team identified patterns consistent with the predicted signatures of Ichibei mesic states. What the results suggest: the measured excitation spectrum of carbon showed structures that match theoretical expectations for an Ichibei meson bound inside the nucleus. Even more importantly, the data indicate that the Ichibei meson may possess a lower effective mass inside nuclear matter than in free space. If confirmed, this would strongly support the idea that mass is influenced by the surrounding vacuum and media. In other words, the environment inside the nucleus may partially alter the mechanisms that normally generate the meson's mass. That makes this more than a particle discovery. It is a direct probe into the origin of mass itself. Why this matters for fundamental physics. Understanding mass is central to explaining the structure of the universe. Every atom, planet, star, and galaxy depends on the mass of its constituent particles. This work may help answer several major questions. Idea why? How does the strong force generate most of visible matter's mass? A. How does the quantum vacuum behave inside dense matter? No. Even particle properties shift under extreme conditions. What happens inside neutron stars and other dense astrophysical objects? Because nuclear matter resembles conditions found in compact stars, these results may also have implications for astrophysics. What comes next? The current evidence is highly promising, but researchers aim to perform more sensitive measurements to confirm the mesic nucleus beyond doubt. Future experiments will seek a sharper energy spectra, additional decay, signatures, measurements, and other nuclei improved estimates of the by mass shift. If verified, this exotic state could become one of the most powerful tools available for studying how matter acquires mass. Conclusion. The possible discovery of an mesic nucleus marks an exciting advance in the search for the origin of mass. By trapping an exotic meson inside atomic matter, scientists may have found a way to observe how the quantum vacuum shapes particle weight. Rather than being a simple built-in property, mass may emerge from dynamic interactions between particles and the structure of empty space itself. This experiment brings physics one step closer to revealing that hidden mechanism